Lunar Regolith. Its enrichment profile kind of sucks. It's basically industrial slag. So then why is it so valuable? Because it's in orbit around the Earth, and any mass already in orbit around the Earth is inherently valuable. You could sell the night soil in your backyard for top dollar if your backyard was in orbit, but it's not. The moon is, which is why the moon is the gateway to forever. Mass from the moon is radiation shielding, it's scaffolding, it's fuel, it's energy. Moon mass is space stations, it's power satellites, it's orbital data centers and seed vaults and life ships and space labs and telescopes and spy and navigation and GIS and environmental satellites and telecom constellations and sun shields and asteroid detection and deflection and nuclear defense and meteor-sized single crystal silicon ingots and flawless fiber optics and orbiting organs and massive fleets bound for Mars and deep space research ships and so much more. Still though, Regolith's enrichment profile kind of sucks. So we need to break the oxides to free the elements and separate all the elements from each other so we have elemental feedstock from which we can forge a future beyond Earth. This is astrometallurgy, and it's my favorite subject because it is so important, so impactful. It is the key to, well, everything. We built the civilization we currently inhabit by manipulating the material world around us, and astrometallurgy is how we manipulate material off-world, so that we can build a civilization in the heavens. Regolith has everything we need, we just need to refine it. About a year ago, I made a video on this astrometallurgy topic which described all the different approaches, and this video got the attention of a scientist and engineer with a quite impressive home lab, equipped with everything from an ultra-high vacuum chamber to a tube furnace to a high-powered infrared laser to a whole bunch of sour cream cartons used for storage, and this person graciously volunteered his time and equipment to progress this field of science.
We have important work to do.
And so, for the past 11 months, we've been absolutely abusing Regolith simulant. Igniting it, melting it, shooting it with lasers, cooking it in ovens, dunking it in water, suffocating it in vacuum chambers, sintering it into donuts, forging it into whatever this thing is, and spanking it till it blushes. Today we will speak with our in-house scientist, going over all these experiments and more, but first let's quickly go over the different astrometallurgy methods so we can get some context to truly appreciate this work. For time's sake, we're going to breeze through these concepts. If you want more in-depth explanations, go watch the first video on astrometallurgy. Okay, so probably the simplest method of extracting resources from Regolith is to just use an impact mill and a magnet to get all the free iron out, magnets and milling. But this method only really gets you iron, which is great, but it's also obviously very limited. And it only gets you the free iron found in Regolith, not the iron found in oxides, which is the majority of the iron, so you have to process tons of Regolith to get any meaningful amounts of iron feedstock. But this method can be done at quite low cost in terms of power, and should be able to be fully automated. But if you want more than just iron, the first true refining method would be that of carbothermal reduction. Look at this chart. This is the Ellingham diagram, which ranks metals according to their ability to reduce other metals. Reduction is the breaking of the oxide bond, and oxygen more readily bonds with some elements than others. So you might think of it as the lower the element is on the chart, the more powerful it is, the better at stealing oxygen it is from the other elements above it. Any metal can reduce the oxides of other metals above it. So calcium metal can reduce even alumina and silica, while iron really cannot reduce anything except copper. But look at carbon. It's quite unique in that it cannot really reduce many things at lower temperatures, but as you increase the temperature, its line goes downwards, so its reduction potential is temperature dependent. Carbon is what we use to reduce iron oxide in the steel industry because carbon is extremely abundant, so it is affordable and effective, but it also creates tons of CO2 as a byproduct. The steel industry accounts for roughly 10% of industrial carbon emissions globally because of this. And because it's such a well-known and mature industrial approach with tons of data and characterization, it of course has been proposed as a method to reduce Regolith. But I sort of think of this as a low-hanging fruit, like it's just copying and pasting what we do today onto the moon. And the problem with this is the moon has hardly any carbon, so it would need to be imported. This might be okay if the carbon could be fully recovered in a 100% recyclable closed feedback loop, but unfortunately this isn't the case. Much carbon is lost in the materials, so This likely makes this the most expensive approach to regolith refining because you'd have to be constantly feeding expensive imported carbon into the process. Not good. Instead, you could use hydrogen, which is much more abundant on the moon. And even if it wasn't, hydrogen reduction should be 100% fully recoverable, so we can have a closed-loop industrial process. Hydrogen is hard to store, but in this case it would be stored as water, as the hydrogen would bond with the oxygen released from the oxide, and water is easy to store. Then, when you want to reuse the hydrogen, you could just electrolyze the water to yield hydrogen gas and oxygen gas. This oxygen gas can then be used for life support, or, more impactfully, for oxygen fuel. It really does seem like there is a strong case to be made for lunar-sourced oxygen being the biggest economic driver of lunar development outside of government funding in the near to medium term. Being able to refill satellites and stations and starships with lunar-sourced LOX in low Earth orbit would be a massive game changer and would really help bring down the cost of rocket launches as well as extend the lifetime of satellites and stations, which is why a lot of companies are focused on this right now. And with hydrogen reduction, capturing oxygen is quite straightforward using very well understood processes. The oxygen comes from all the oxides that are listed above hydrogen on our Ellingham diagram. And at a certain temperature, that includes iron. And what this means is that hydrogen reduction should be able to yield all the iron in the regolith, not just the free iron in the case of the milling and mining method. So you get more bang per kilogram. But of course, as you can see by looking at the diagram, hydrogen is still limited in what it can reduce. And we want, well, pretty much all of the elements in regolith because they're all extremely useful. Aluminum for electrodes and reflective surfaces, and silicon for solar cells and other semiconductors, and titanium for structures, and chrome for corrosion resistance, just to name a few. Perhaps the most straightforward method to getting all the elements is to use fluorine. The reason everything is bonded with oxygen forming oxides is that oxygen is the second most electronegative element, second to fluorine. Fluorine is the most electronegative element, but there's a lot more oxygen in the universe than fluorine, so we have a lot more oxygen minerals than fluoride salts, although we do have a lot of those too. This is different from reduction, where one thing steals the oxygen from another. In this case, the fluorine is a homewrecker, stealing the element from the oxygen. So we don't get fluorine bonded with oxygen gas and a bunch of elements. Instead, we get all the elements bonded with fluorine salts, and oxygen gas, and then we can do these processes to remove the fluorine from the elements. This method of refining regolith was proposed by Dr. Jeffrey Landis, which I explore in depth in another video. It's a good process, but it's a bit complicated. However, you should be able to get every element separated and yield oxygen gas, and do so at relatively low temperatures with relatively reasonable power requirements. Fluorine isn't abundant on the moon, so it would have to be imported. However, this process should theoretically be 100% closed-loop fluorine recoverable, so you don't need imports to keep the process going. Any imports would simply increase your capacity to refine. But fluorine's ability to bond to everything is also its downside. It is kind of like the chemical nuclear option of refining. It's able to reduce everything quite rapidly, including your life expectancy, which means two things. First, the entire system would need to be imported, not just the fluorine, since to avoid being melted by the fluorine, its components would need to be made of nickel alloys, and nickel is not common on the moon, despite what many early Apollo analysts reported. You'll see a lot of early regolith characterizations saying there is a lot of nickel, even as late as the 1980s, but this was due to contamination from their nickel-coated tools. That's just kind of a funny side note I thought I should mention, but in reality nickel isn't that abundant on the moon, so each fluorine refining unit would likely need to be built on Earth and shipped up to the moon, so it wouldn't be very scalable. Still though, it seems like it could maybe be quite a promising first step. I mean, sure it's complicated, but having the ability to pack an entire process into one box, regolith in one side, elements and oxygen gas out the other, seems quite useful to get the ball rolling at least. And sure, that might be true, except the R&D on actually developing this today would probably be quite costly, as fluorine is so dangerous, only a few labs in the world are equipped to handle it, and there's only a few suppliers, and the safety standards are quite rigorous. So that exists as a sort of roadblock to even trying to develop this thing. I mean, it probably could be done if someone really wants to, but it's a tall order. And anyways, if you're willing to embrace complexity and single imports for a first generation refining unit, then you might as well embrace aqueous chemistry processes which are somewhat on par with this fluorine process, but use much more accessible, much less terrifying solutions. This is a general categorization that includes all the closed-loop, water-intensive wet chemistry processes we typically use in mining today. So we won't go over all of them, but an example is the sulfur silica process. The downside to these is they would probably end up taking up quite a lot of volume and mass, as they would basically be a mix of specialized processes for each element, and would require lots of pumping and slushing and flushing and draining and filtering and piping and heating and cooling. As far as I know, these processes or combination of processes have not been that explored for regolith refining very much beyond hypothetical outlines because of their obvious drawbacks, and the fact that we just have more promising avenues of approach. Probably the most explored route is that of using molten oxide electrolysis, or MOE, which basically just uses electricity to brute force break the oxide bonds with electrons. If you watch my channel, you're likely aware of this process, and if not, you may have heard of it as a solution to that whole steel industry carbon pollution problem, as this process is being developed as a green alternative to steelmaking, with the company Boston Metals doing a lot in this regard. A lot of space companies are also considering it, not necessarily for regolith refining, but as a means for generating oxygen on the moon from regolith, because this method has pretty high oxygen yield and a high TRL maturity rating. However, there are two big problems with this approach. First, it's questionable how precise one can be in extracting pure elements from each other. Sure, it's good at reducing things, but then what you're left with is an oxygenless metal silicon slag alloy. So how do you get the silicon separated from the aluminum, separated from the iron, and so on? Well, you could try to set the voltage to match that of the electron potential of the individual elements, so just that element collects on the anode. However, you probably need an overpotential, so this level of precision can be tricky. If you're confused about what I'm talking about, again, I recommend watching my first video on astrometallurgy where I explain this concept in more depth. Anyways, the downsides to electrolysis are that it requires lots of electricity, and there are problems with corrosion of the electrodes and the refractory materials inside the reactors. Dr. Ignatiev and Dr. Sadoway at Lunar Resources and Boston Metals have developed a method of thin film depositing iridium onto anodes so they aren't consumed as fast or at all. But this does probably mean the anodes will still need to be imported, or at least the iridium, and maybe the internal refractory lining for the reactors. So we can categorize electrolysis as having a simpler system design, less imports, good oxygen yield, high TRL rating, but it likely still needs some imports, has a high electricity consumption, and a more involved process for getting purified elemental feedstock.
Previously on Anthrofuturism.
Sublimation. When a solid changes directly into a gas, skipping out on the liquid phase entirely. In other words, at these temperatures, in a lunar vacuum, our molten regolith would not be molten at all. Rather, it would be a vapor. I knew this was possible at some point, like around the temperature of the sun, but I would never have guessed it could happen at these temperatures. And look, nearly every oxide subliminates or boils completely around 1400 degrees. Iron around 1100. This is just absolutely insane when you realize our original electrolysis process, like the one employed by Lunar Resources and Boston Metals, has an operating temp of 1600 degrees. And this isn't even the lowest vacuum diagram. This is 10 to the power of negative 10 atmospheres, while this chart, 10 to the negative 15, represents the pristine lunar environment. So the sublimation temperatures can actually be even lower. Could this really be? Could we really just vaporize regolith at this temp and then distill the constituent elements individually? No electrolysis needed? It seemed too good to be true, so I tried to see if there was any prior research into this that might give me a better sense of what the hell was going on here, looking for reasons why this wouldn't work, but instead I found 2 studies indicating it would. These are the sweetest words I've ever read in my life. Quote, "Vacuum pyrolysis is based on the vaporization of metal oxides that simultaneously reduces the oxide and produces oxygen gas. The reduced oxide can be condensed out of the low pressure gas at temperatures below 500 degrees Celsius, while the oxygen remains gaseous." But what really induced a sudden and dire need to change my pants was this statement. any type of lunar regolith or rock can be used. Nearly all lunar minerals will vaporize and release oxygen when sufficiently heated. This oxygen can be separated out by fractionally distilling it. The metals and reduced oxides condense while the oxygen remains as a gas. Since the process is entirely thermally controlled, a solar furnace can be used, and no materials need to be brought from the earth once the plant is operational.
And Jesus wept, for there were no more worlds to conquer.
In other words, we can selectively reduce oxides based on temperature. In my opinion, pyrolysis is the holy grail of astrometallurgy. The idea here is that in a vacuum, we can sublimate the oxides by just simply setting the temperature, and then we can condense the elements and the oxygen separately using different cold temperatures according to their condensation points, like a cold finger or a distillery, or molecular distillation for you lab rats, or fractional distillation for a more industrial scale of vision. The stronger the vacuum, the lower the temperature required to sublimate these oxides. Look, here's an Ellingham diagram for 10 to the negative 5th atmospheres vacuum. Here's 10 to the negative 10th power, and here's 10 to the negative 15th. The moon's vacuum is around that negative 15th power, and even after the Apollo astronauts stirred up dust, the vacuum was only lowered to 10 to the negative 13th power. So I often reference the negative 10 data as a decently conservative estimate. And I think it's the holy grail of regolith refining because we have free vacuum and abundant thermal energy, and it does not require any imports. And this lack of imports and its theoretical capacity to have quite high yields means it should be extremely scalable. So when I imagine an industry in space and on the moon, I imagine pyrolysis furnaces. And for the intense heat required, we can generate these temperatures using mirrors, a solar furnace. Things get even more promising with pyrolysis if you consider reducing the regolith beforehand. As you'll notice on the diagram, metals sublimate at much lower temperatures than oxides. And if you look at the bottom of the diagram, you'll see calcium is the major reducing agent. And fortunately, we have lots of calcium on the moon, more than even hydrogen. So the idea here is to use it to reduce everything into an alloy cake with calcium oxide. This can be done easily as an exothermic reaction. You know thermite reactions? Well, those happen because aluminum can reduce most things if you get it hot enough. And as you can see on our diagram, calcium is below aluminum, so it's like an even more extreme thermite reaction, a calciothermic reaction. So we reduce regolith with calcium metal and do this pyrolysis process at much lower temperatures. And then the only oxide we would have to break would be that of the calcium oxide. So this is really promising. I mean, I really want to emphasize this calcium stuff because I've heard of groups exploring pyrolysis and then abandoning it because the oxygen yield wasn't as high as electrolysis. And they're going for oxygen because of the ability to sell it. But I am also sure this is because they weren't able to free the oxygen from the alumina and silica, which are common refractory materials and require about 2000 degrees to thermally decompose. And these two very stable oxides make up about 25 to 35% of regolith. So if they're just trying to do straight pyrolysis on regolith and they're not getting up to 2000 degrees or more, then of course they're not yielding that much oxygen. But if you reduce regolith with calcium first, then you have all the oxygen in calcium, and then you should be able to yield close to 100% of the oxygen from the calcium oxide. And it gets even better because this calcium redox reaction, again similar to a thermite reaction, should itself generate a ton of thermal energy, essentially preheating your regolith before sublimation. And it might even sublimate some stuff on its own here at this step, which may actually be a problem, but one I'm sure can be managed and is definitely worth the free thermal energy. So, isn't that awesome? It's so exciting. Except, well, unfortunately this hasn't really been tested at all, to my knowledge, until now. That, ladies and gentlemen, is elemental calcium retrieved from reduced regolith under vacuum with an infrared laser.
Hey, how's it going?
Hey, Robert, ready to tell the world about our experiments?
Absolutely.
Awesome. So I figured we should just jump right into it. So the first thing we needed to do was create a simulant to work with. And since we were doing a lot of experiments, kind of needed a lot of it. But simulant is quite expensive, like $50 a kilogram, which if you're a government-funded lab with deep pockets is no big deal. But we're sort of the furthest thing from that here. I mean, this is garage science. So what we did instead was we used XRF data from Apollo to make our own simulant. And we also bought 1 kilogram from a distributor to make sure ours was as good as professional grade simulant sold commercially. And in some way, I suspected ours may have actually turned out a bit better, like with titanium contamination, but I'm getting ahead of myself here, and I'll let you talk about that later. Anyways, creating the simulant was more than just mixing oxides together in a sour cream can. Would you like to elaborate a little bit on the preparation work that was done to ensure our samples had high fidelity?
Absolutely. Well, the sour cream container is the most important. I'm just kidding. I'll start. So yes, exactly. One of the things that we need to do is simulate as best as possible the lunar environment. When you receive the simulant from whether it's SRT or you're making it yourself, one of the things you need to do is basically give it a round of what I call the lunar treatment. First, we took the simulant, we subjected it to 9 kilovolts, 230 or approximately 300 milliamps for approximately 30 minutes or so to make sure that the particles are all pretty much they're the even charge. After that, we took it to the vacuum dehydration, where we heated it up to about 200 degrees Celsius and performed vacuum dehydration on it. From there, we purged the system with argon. Then we canned them up and stored them in a mild vacuum chamber under argon for our next process.
So then the first refining experiment we did was carbothermal reduction, not because carbon is common on the moon, but because it's sort of the industrial standard for bulk reduction, namely for iron oxide in the steel industry. And for that reason, despite the fact there isn't much carbon on the moon, we still did this to get a strong benchmark, which we could compare to the other more experimental reduction methods done later. And the results were, well, unsurprisingly good, right?
Yes, the carbothermal reduction actually worked extremely well. The results were pretty much as you would expect. It's an industrial standard. It's also a good comparative sample that we can use against some of our other processes. One of the reasons that we entertain this idea is strictly because, one, it's very simple, it's industrial, and two, if there is any methane that might be left over from any fuel processes, the carbon in that can be used for that. I personally don't think that that's the best use of carbon on the moon, but it is one of the methods, so we explored it. And the results were pretty much typical. It reduces it very well.
So then a more friendly ISRU approach we did was to use hydrogen, which is a very effective reducing agent, and we should have it on the moon. And it's fully recoverable, meaning fully recyclable. However, it's somewhat limited in what it can reduce. For instance, it can't reduce alumina, silica, titanium oxide, calcium oxide, everything below it on the Ellingham diagram. But importantly, it can reduce iron, and quite effectively, correct?
Yes. When you're thinking about a process and you probably want to grab everything that you can out of the lunar regolith, one of the first processes that you probably want to go across is your iron. There is a limited amount of free iron, and that free iron is also bonded to a lot of FeO, iron monoxide. So one of the processes that we explored was a vacuum hydrogen reduction. We found that it actually reduces iron extremely well. And one of the main reasons we went with this is because you're not only producing iron, but you're producing oxygen from the lunar regolith, which is a valuable product that can be sold. You're getting any helium-3 that might be bound in the lunar regolith through a very simple process, as well as you're beneficiating the lunar regolith for your next processes, meaning that you've removed the iron, there's no more iron. It effectively reduces all the iron oxides into elemental iron. It also does this at a lower temperature, meaning the input energy for this process is a lot less. The byproduct from this process is H2O. Obviously, you're using hydrogen and it bonds to the oxygen, and that makes water. Then essentially you recover all your hydrogen and any input that might be in the regolith. If there's hydroxides bound to the regolith from hydrogen coming in from the sun, you're going to recover that as water. So you're going to have a positive input of water. You're going to have a positive input of oxygen, and you're going to have a reduced metal out of your byproduct. Because the temperatures that you can do this are, a lot lower than the typical processes you need to actually melt iron with, you're able to keep the product anhydrous, as well as you can remove the iron magnetically right after the process. This kind of has a lot of benefits. One, lower reduction in energy. Two, you have positive oxygen and hydrogen output. Three, helium-3. Four, reduced iron.
Yeah, and I sort of expected it to be like glassy, but it ended up being sort of like quite fluffy, which seemed to make it easier to kind of just use a magnet over it to pull out the reduced iron.
Yes, a simple electromagnet would work. Any magnet of any kind. Iron's extremely magnetic. And yes, we tried obviously different temperatures. I have temperatures here. We tried everything from 1550 degrees Celsius, which did create a glassified regolith, and at temperatures that were much lower. And we tried at 750 Celsius. It was pretty much like sand. It was free flowing. The particles were not stuck together. We did attempt sintering lunar regolith to see what temperatures it would actually fuse at. And we did find that like around 1042 Celsius is when an optical change occurred on one of the samples, and then pretty much no optical change on some of the other samples as far as glassification until over 1150 degrees Celsius. So there's optimal ranges to produce the pure iron without melting it, which is extremely useful. If you think about SLS printing, we have powder bed printing. We can, at this point now, which is going to be difficult to do on Earth because of the oxygen, but in lunar environment would be absolutely 100% doable, is to print out with a laser any parts that you would need out of pure iron, or any of the alloys that you might want to mix would be a lot easier to mix as a very small fine powder to get the proper ratios and vibrate them together, as opposed to, the processes of mixing alloys and melting them and then separating them into powders and using that for SLS. So it does have a lot of benefits in that aspect. You're not just reducing iron, you're getting a lot of the other products you might want from the lunar surface.
And what were those optimal ranges? I remember that one paper, and I think it was Maria Regolith. It was 950C was like optimal.
Yeah, I'm looking at Highlands right here. 120. So at 970C on mine, I saw optical change up until 970. So from 970 to 150, no optical change. In the end, furnace temperature on the sintering furnace isn't as accurate as the other furnace. So what is 970 is probably 950. They're pretty close.
Okay, that makes sense. Yeah, because above 950, that's when bubbles started to cause porosity. So.
Yeah, so between 950 and 1050, I saw sintering basically. And then over that, I still saw sintering up until 1120. Didn't really see glassification until 1550.
Okay, cool. Yeah. And then we found reduced titanium.
Yes, we found titanium in 2 of the samples. They were actually reduced at higher temperatures. They were at the 1550C. So typically hydrogen doesn't reduce titanium. However, there has been some studies and research that does show that it can reduce when other elements are present, as they act as some function of a catalyst. But to be honest with you, the amount of titanium that was seen could have been an impurity because it was shown in the SRT product and not in the other simulant. So that's an anomaly we need to research.
Yeah, I wonder if it was like the feedstock they were using or part of their equipment. It's interesting, titanium.
Yeah, it could have been part of their milling process. It could have been just from their source. A lot of titanium, ends up in the environment. It's pretty common, especially titanium dioxide is very common, but reduced titanium, it's a little bit more common than you would think, as far as like you're using an impact mill or whatever process you're using to make the regolith to its uniform form. You're making it a mass, you're selling it. It's very possible that this is some contamination of some kind along the way. So we just need to do some more research and probably get some quantitative analysis on that one. It really
more research than N equals 2.
Yeah, exactly.
And then you mentioned getting helium-3 from this hydrogen reduction process. How does that work? Helium-3 is quite inert, so would it just kind of separate out, or how it wouldn't bond to oxygen, so then it would just be like a separate gas? Do I have that right?
Yeah, so basically, because it's inert and because of its density, its mass, it's going to not interfere with any of the processes. It will be extracted within the process and it will be stored with the oxygen. The way to recover it from that is very simple. You have a cylinder in your process where there's physical separation over distance, meaning that, if you had a tube coming off of, like the same way helium floats up in a balloon, it's going to float up to the top of any process. So you would collect it off of that. You would siphon it off of that through a vacuum process. And since we're going to be working in pressures that are more positive than the lunar environment, the process is straightforward.
That makes sense. And I know helium-3 is often touted as a solution to fusion, but I've heard that its real application is in quantum computing for cooling.
Yeah, so basically today we use it to obtain really, really low temperatures. Basically, you're using 2 isotopes of helium in a dilution refrigerator to achieve these temperatures to get rid of noise, basically. The way it works is almost like a Joule-Thomson cycle, where you have 2 gases of different densities. You use obviously processes to get down to a level of temperature that you need for helium-4, and then you use the other isotope, which is a lighter isotope, and in this process, which basically makes it, things to as cold as we can kind of get them here on Earth.
And I know a lot of people say quantum computing has no real future, like Sabine Hassenfelter, but it seems like they don't actually know what they're talking about.
Yeah, there's a huge future in quantum computing. The quantum world around us that we are still very, very new to discovering has a lot to offer if we can find applications for it. Currently, there are applications for everything from magnetometers for NV sensors to periodic pulling lithium now. But I mean, this is a whole nother subject in itself. But there are actually applications today that are used, and there are applications that require extreme fidelity from their sensors, which you cannot just make any other way. There are applications from everything from low-cost data storage, extreme density data storage, to as far as the amount of time you can store data as well. As far as computing processes, there's also those as well. There are magnetometers now that are used from everything from bomb detection to MRI machines that change lives every day. There's applications. If you think about it, your computer, it's functioning almost at the scale where, the quantum level starts to become, we need we're hitting Moore's laws, and we need to figure out different ways of processing our massive amount of data, and we need to figure out how to do it in faster ways with less power. That's where quantum computing is really gonna shine. It's probably gonna change the world, and it's not gonna be, we're not gonna have enough power to, for AI to evolve or whatever. It's going to be, now we have plenty of power because our processes aren't requiring the same resources.
Yeah, so I was sort of skeptical about Helium-3's applications for fusion, just because I know there's alternatives, and it's like an efficiency increase for some, like the tokamak fusion systems. It's like, it gives you an efficiency increase, but when you consider the cost of importing it from the moon or space, the economics don't seem that promising for that. So I was skeptical about its applications for fusion, but it sounds like it might actually have a promising future. Like, it's almost been revived as a potential lunar, moon gold, basically.
Well, one of the things with helium-3 is it's just incredibly rare. I mean, helium, even here on Earth, is pretty rare, but the isotope helium-3 is incredibly rare. And the reason that it's, looked at as, kind of a new resource to obtain is because of its unique properties. You can obtain, like I said, extremely cold temperatures, but there are other things. A system that uses helium-3 for its cooling, like, let's just say an MRI machine, the fidelity would be a lot more. You're able to get less noise in your machines. The more you're able to filter out noise in a process, the closer you can get to a pure process. So everything from, you name what these things can be used for, everything from bomb detection to communications to, it's really phenomenal, the applications that can benefit from this fine-tuning these processes. So there's also a limit on, how much of it we have on Earth. So there's a finite amount of it on Earth, and getting it from the moon surface seems to be a priority for some companies, and it's a product. So, if it doesn't take, anything away from the refining process, it's just a bonus. Another thing when you're dealing with the hydrogen reduction is, you're not really dealing with cryogenic storage, or you're dealing with like atomic water. And when you need it, you electrolyze it. You're not dealing with hydrogen embrittlement, high pressure vessels, cryoplastic vessels. There's your hydrogen and your oxygen. It's kind of all wrapped up in that nice little process.
Yeah, your hydrogen, your oxygen, your helium-3, your iron. It doesn't get everything, but it seems to solve a lot of big problems very easily.
But it's one step in the process that you would use to, end-to-end process. The next process that you're probably going to want to look into is, calcium.
Yeah, it's the ultimate reducing agent. I mean, it's at the bottom of our Ellingham diagram. It's even able to reduce alumina.
Exactly.
And we actually have quite a lot of calcium in its oxide form in Regolith. And so we actually tested it to see if calciothermic reduction would work on Lunar Simulant. And, well, I thought the results were really nice. I got really excited, maybe a bit too excited. Maybe I'm a little bit of a pyromaniac, but for me, just seeing the reaction happen and realizing that this is real, like it actually works, seeing the Ellingham diagram in action and that sometimes theory on paper actually does translate into real physical results was just so cool. Anyway, sorry for fangirl monologuing about our calcium reduction, but what did you think about the results?
Well, the results were pretty much, they were expected, but a little bit more than expected. The results were pretty impressive. It did reduce the alumina into aluminum, which separated out in the slag. The mass is separated very easily. So the leftover calcium oxide, absolutely recoverable and can be turned back into calcium. And the product afterwards, we tested two different ways. We tried hydrolyzing it and we tried an acid. They both were clear signs that it was reduced aluminum. Along with, I believe we have some microscope took pictures of it as well. So yeah, it was pretty interesting to see the self-sustained, reaction. Basically almost a thermite reaction. It is a thermite reaction with lunar simulant.
Yeah, and that it's exothermic in nature, so it gets up to pretty extreme temperatures, which kind of serves almost, if you're going to do pyrolysis on the slag later, it's like a preheating step in a lot of ways. You might even get some sublimation from this step alone, which could actually be a problem if you're trying to recover everything, but I'm sure it's manageable. But just like that free energy you get, well, I guess, we already get so much free energy from the sun in space, so.
Well, the oxygen bound to the regolith is a form of energy in itself. The exothermic reductions, you can manage the heat from those and use them for your other processes. And as far as the vacuum is a great insulator of heat. So in processes, you want to keep heat in for efficiency reasons. It costs energy to lose heat out of a system. So the only heat you really want to lose out of the system is through the regolith itself. Using that as your working medium to remove heat from a system, you can pretty much have almost like a conveyor system, or if not a vibrational system, where it's a non-stop process, at least during the lunar day while there's sun.
And then we got somewhat of a natural slag separation where the alloy cake separated from the calcium oxide and the silicon. Where the calcium oxide and the silicon were bound together though, right? But I think that was because of the hydrogen in the atmosphere, since we didn't do this calciothermic reduction under vacuum, sort of violent.
Yeah, but there was a more atmospheric oxygen for it to react with, so it created higher temperatures, which created some of the silica diffuse.
But if done under vacuum, which this is still theoretical because we haven't done it under vacuum, thermite reaction basically. But theoretically, the calcium oxide should completely separate from the alloy cake.
Oh, absolutely. And most of it did in our process. We just did find that there was some silica bound to the calcium oxide. That's also because the simulant itself was not beneficiated. Had we done it with beneficiated, like we had removed the iron and removed the silica, then yes, the reaction would favor towards the oxygen bound to the regolith, as opposed to in the atmosphere. And this process is going to happen with some kind of a pressure. It's going to be extremely low pressure, but the process itself is going to release outgassing, which is going to create some type of pressure. So there needs to be some more experimentation as that as well. The problem is that, you're doing an exothermic reaction in a vacuum, and that reaction itself is really hard to manage if something goes wrong. So pretty much need a dedicated unit to try that. That's going to end up being ruined.
Yeah, you're essentially like setting off a firework and $10,000 equipment. It's like not.
Yeah, the last thing you want in a laboratory is those reactions happening, especially unwanted. Even if they're in a controlled manner, they're typically, they reach temperatures that are extremely destructive to equipment.
Yeah, and that was sort of the barrier to testing pyrolysis in ultra high vacuum, but we did find a workaround. But before talking about that, I wanted to comment on how you characterized the reduced alloy cake. You did hydrolysis for characterization, right?
Hydrolysis, and also we looked at it under a microscope. We did hydrolysis, and we tested for aluminum using, if I remember correctly, I think sulfuric acid. We put in an acid where the oxide would not react and reduce metal wood. So it showed hydrogen production in that, which we lit with a lighter, showed hydrogen. Yeah, so that's definitely aluminum. But it was very clear to see that it was aluminum to begin with when it was hydrolyzed, because it reduced back into the calcium oxide separated from it.
Of course, though, the big question is how to then reduce the resulting calcium oxide to return calcium metal so that it can be reused, and whether or not this could be done with pyrolysis, or if we would need to use something like molten salt electrolysis to return the calcium. And it looks like pyrolysis should work. But before discussing that, I wanted to quickly venture into a sort of side quest you did, which was to see how easy or hard it would be to make glass from regolith. I mean, glass is really useful for all sorts of things, not just for windows. It's a great insulator and can be used for solar panels and a lot more. And the Highland regolith, which is high in silica and alumina and low in iron, proved to be somewhat of a decent glass feedstock, right?
So we used basically hydrogen and oxygen to reach the temperatures that we needed, and we beneficiated the regolith with a magnetic benefication, and we reduced the simulant, and it produced an extremely tough amorphous substrate. It is about as tough as you can get. Basically, it's fused silica. It's clear, so to the visible spectrums of light, which is very important if you're going to be using it for any solar processes. But also, it was extremely hard. You think about like glass as something that's like fragile, but But this is harder than most metals. And we tried destroying it and was not able to with a sledgehammer. I was able to crack it, but it definitely dented the sledgehammer, and it took several tries. Before with the sledgehammer, we tried a hammer, couldn't break it with a hammer. We tried a hydraulic jack, couldn't do that. Well, got to a point where we were like, okay, let's use a sledgehammer. And the sledgehammer basically put a nice dent in a piece of concrete and the hammer itself.
That's crazy. And I mean, yeah, Fusilica was used as like the windows on the space shuttle because it could withstand the re-entry temperature and pressure. But it's also been used for, lenses and fiber optic cables. It's incredibly useful all around. It could even be used for construction. It's a good insulator for electronics.
Oh, absolutely. It's a great insulator. It's clear. It's very strong. It has all the properties that you would want with glass, other than it's extremely high temperature that you need to get to that point. If you're using hydrogen and oxygen to melt this, you're recovering the hydrogen and oxygen in the same manner. You're able to reach those temperatures. That's the only main difference between the glass that we know here on Earth and what you would have up there is that our processes here are kind of industrially made for ease of manufacturing. One thing that is going to be a little bit difficult is how you're going to be able to process that, because it's not going to free float like most glass will. At least in my experience. It's even while it's red hot, it's malleable, but it's difficult. So it requires some machining probably. However, it's a great construction product. It's an extra electrical insulator. It's Windows fiber optics. You name it. It's one of the first things that man's mastered as an oxide.
And then speaking of insulators and lenses, we also explored laser sintering of the bulk regolith, where you made some awful tasting but quite interesting looking laser donuts.
Yeah, so one of the things that we explored was how can we get like the hottest temperatures that we can with the least amount of energy, and lasers kind of makes a lot of sense. Lasers, they work really well. They can focus a lot of power into a very small area, especially a pulse laser. So we went with a fiber pulse laser, and we found anything that's dark absorbs light really well. It's pretty easy to turn into a glass substance. With more power, you can vaporize this stuff. So keeping it in a glass phase is very similar to SLS printing, and the object you're making is basically glassified basalt. It's actually incredibly durable, and it can be done extremely fast. There's really no limitation on the designs that you can do, and since you're steering a beam using mirrors, there's no moving parts.
Yeah, and so using a galvo laser, you're able to control the beam using mirrors instead of like a mechanical rotating axis. You can use mirrors, and so you're able to get very precise and unique shapes and geometries.
You can make pretty much any intricate geometry you like. Basically, you use the same method that you would for printing any metal parts that you would from the iron feedstock. Basically, you focus your laser into the area that you want, and it heats up the material. And with the pulse laser, you're able to do this at incredibly fast speeds. So you're able to keep that heat in the material. In vacuum, it works actually a lot better than it does in atmosphere because of the insulated heat. And you can actually draw things like objects, solid objects. It could be anything from roads to landing pads to habitats, all the infrastructure that you would need that is, basically going to be comprised of glassified or sintered regolith can be done, externally with a laser a lot easier with a lot less energy than pretty much any other process I can think of.
Yeah, and with the pulse delivery, you're able to get kilowatt class peak power from just tens of watts, right? Yeah,
basically a 30-watt fiber laser can deliver several kilowatts of power. You're using time as a factor. Basically, your pulses are in the nanoseconds, but they're delivering kilowatts of power. And you can adjust these frequencies up and down to deliver different amounts of heat into an object, as well as the steering speed of the beam, how many pulses, your kilohertz rate, focal rate. So there is a lot of these parameters that you just can't stick a laser onto some regolith and think, okay, it's going to reduce or it's not going to, explode all over the place and ruin your lab. It's probably going to happen your first time, but with some fine tuning, you can actually do some reduction. You can do some pulse deposition. You can definitely sinter. It's a very useful tool as well.
Right. And it's great for electronics or precision, but because you're able to achieve kilowatts, but like in a nanosecond. So it's like heating things up to 5,000 degrees, but it's a tiny amount of matter. So they're great for electronics and precision, but not ideal for bulk refining or processing.
Yeah, it's not exactly a nanoseconds. It's in the nanoseconds range for some of the higher peaks of power and less for the lower peaks. And yes, this is something that you can directly write, your process to your substrate. Like if you're doing, let's say, a substrate where you needed deposition for a back electrode, or you needed electrodes on an insulator, or you needed to create a circuit, something like that. That's a great process for it because you do have like micron precision over this beam, which is also very small in diameter, probably only a few microns in diameter. You don't really want to do this in an industrial process because you're going to need a lot of lasers and you're not going to get a lot of end products. But you do have one tool that does all these things, which is kind of important for the initial beginning or research or phase of any type of development.
When I saw these laser donuts, I immediately thought about like parts replacement, or not really parts replacement, but where you could basically send the exoskeleton of a part, just like the metal parts, and then you could fill it in with like sintered regolith discs or bricks as the structural parts that the joints would basically push off of. And this way you could get like a massive mass savings for your rocket imports. That way, I mean, you could import like 10% of a vehicle and then fill out the rest of the mass. Like we talk about filling ballasts, like some vehicles need to be heavy in order to leverage their own weight against the mass that they're moving. And so we talk about like filling bags on the side of them with regolith, so you're sort of getting in situ weight. And this would be like, with your laser donuts, it would be like a next level of that, where you're not filling like bags with dirt. You're like actually building half or even more of all the dumb parts, all just like the bulk mass parts with, you know, very just centered classified regoliths. Anyways, food for thought. That's just what reminded me. That's the first thing I thought.
You know, if you think about it, you know, those cylinders line up nicely to make a nice tank for storage of any kind. The amount of mass that you would need to bring from Earth is going to change. Is it going to be easier to take a skeleton of something to the moon? Or is it going to be easier to take only a small amount of powdered metal that you would need, that you can't get in situ, maybe for the electronics or whatever? And like, you know, a bag of powdered metal is going to be a lot easier than like, you know, the final product of, even if it's an exoskeleton. So with the ability to be able to lie down, you know, your, let's say, iron powder bed, and your laser comes wrong and prints your structure, and then you fill it in with your, you know, glassified regolith or whatever, the amount of mass that you now need to bring from Earth is reduced from tons to grams, and it changes priorities. Now, maybe like phosphorus is very important, or boron or something like that, where you know, before they're like, oh, we only need so little of that. But now we're thinking, okay, we're gonna make, you know, 1,000 miles of solar panels or something. Your options change. If you can bring the refined product itself and build it on the moon using laser accuracy, then why even construct anything on Earth to bring it to the moon? Just bring the raw resources, right?
Yeah, so you just send one laser to the moon, and now you have your landing pads, you have your SLS metal printing, you have your, you know, your everything. You have so much, not everything, but you know.
Yeah, when it comes to actual like metallic stuff, basically powder bed, you know, printing for any structure is going to work perfectly in a vacuum. And the amount of time that an object will hold its heat, and the amount of time you would have to shape something or to print it right is, you know, and since it's already being printed on regolith, there's your cooling medium right there. I mean, you know, it's kind of perfect.
And then speaking to the usefulness of lasers, from the beginning of these experiments, we were sort of perplexed as to how we could test pyrolysis without ruining your expensive vacuum equipment. I mean, we're literally talking about putting dirt into an ultra-high vacuum chamber used to sputter semiconductors and stuff. And even if that wasn't an issue, getting the intense amounts of heat required for pyrolysis, over 1,000 degrees Celsius, in that chamber without damaging it also seemed impossible. But then you had the idea that we could basically make tiny, cheap vacuum chambers with test tubes, and that we could use the laser to generate the required heat to sublimate the regolith. And so this could be another route to refining, laser sublimation, but it could also serve as a sort of surrogate for pyrolysis. An imperfect one, sure, but one in which we could test the viability of controlling specific temperatures to target specific elements, as we would theoretically want to do in a pyrolysis furnace. And theoretically, we could set the temperature with the laser by varying its settings, as each oxide has a unique spectral absorbance. So by adjusting the laser focus and frequency, we might be able to target each oxide according to its spectral absorption properties, right?
Yeah, pretty much everything except for silicon dioxide because of its clear nature. The wider the oxide is, the more difficult, the more reflective it is, but that actually helps you separate some of the other oxides due to their, you know, spectral absorption. So you can selectively, you know, choose which oxides you are, because you have this micron precision just by their reflected energy of light and their spectrum. You could do selective oxide reduction. So we tried this by basically taking a roughing pump and hooking it to a vacuum tube. In the vacuum tube, we would have an aluminum scepter to help prevent, you know, any heat transfer into the glass from our samples, and we tried pretty much everything. What we found is obviously the silicon dioxide is transparent to the IR wavelength that we're using, so it worked out perfectly. So basically, what you do is you have different reflectivities of different oxides, different spectrums of it. So you can selectively choose which ones that you want to sublimate. We did this we started out with pure oxides, and we were able to reduce some of them. We used basically an aluminum scepter in a test tube with a roughing pump, and we had our vacuum chamber in each test tube. We were able to not have to worry about damaging the equipment. So we were able to do a lot of different samples. So we did everything from all of the simulant samples to the individual metal oxides. What we did find is that some of these metals will absolutely reduce by laser under vacuum. They don't have enough time to bond back with the oxygen, and they deposit on a cooler surface. We've had really good success with iron. We've had some success with magnesium, alumina, and we're currently working on calcium. We also found that in some of our samples that some of the metals actually fused with the silica, creating an extremely well-preserved crystalline substrate.
And just to clarify, you went through and you tested on individual oxides to figure out the optimal laser settings to reduce that specific oxide. So you had a whole bunch of different test tubes, and each one of them you put the pure oxide, like calcium oxide or titanium oxide that we would find in the regolith, and then you figured out what the settings were to reduce that. And so by doing this, you built up a settings library essentially for your laser, right?
Correct. Basically, we needed to find out what settings and what actually would reduce and what didn't reduce, and what parameters we need to actually have that happen. So in the beginning, basically, if too much power pushes everything away, too little power doesn't do enough. Just the right amount of power, just the right amount of spearing speed, just the right amount of pulse width, depending on the actual oxide, can get it to reduce. And so by dialing these in, we're able to take the actual bulk simulant and do some selective oxide reduction, where basically we were able to reduce iron and magnesium separately from everything else. We got those two at the same time in the same tube, using different settings for those different metals. So I took titanium and iron, tried them individually, and then we mixed them together. Basically had them one side of the test tube iron monoxide, one side of the other is titanium dioxide, and we were able to reduce both of them in the same tube using different settings while they were in intimate contact with each other, which was kind of impressive. The iron showed electroconductivity. The titanium, not so much. It was in the mega ohms. If not, it was not exactly conductive. However, we did show that we were able to get some titanium reduction with some conductivity on other samples. It's a little bit more difficult when they were intimately combined because of the nature of the two colors. One is extremely dark. We were using pure oxides, so a lot darker than you would have on the moon. And then the other one was bright white. So in showing this, that it's possible, it just needs to be fine-tuned.
So it's possible to have mixed oxides and then to selectively, sublimate them with this laser. And that's incredible because it's like you're putting together you got the settings from the oxides and then you mix the oxides together. You didn't do all of them, but you did multiple of them, and you were able to get selective sublimation even though they're together.
Alumina was pretty difficult. I'm still working on that one. It has its inherent problems because of its reflectivity and its very extremely high temperature and reactivity. But the other metals, absolutely. Magnesium, actually incredibly easy. Iron, incredibly easy. Titanium, a little bit more difficult due to its color, but absolutely was able to reduce that, as well as calcium.
And then you mentioned the electrical conductivity. So you were measuring the ohms, like the resistance of the metal deposited onto the test tube. And do you think that the titanium had higher resistance because it fused with the silica from the test tube itself?
I think the titanium had a lower conductivity because it had a lower ablation rate. So there was less of amount deposited. Obviously, titanium's less conductive than some of the other metals, but it's also, because its ablation rate is less, was deposited onto the scepter, and so we found that in the mega ohms. We did find actually everything from a range. I mean, iron was anywhere from ohms to kilo ohms to mega ohms, depending on whether it did fuse with the silica or not. That was the test tube, silicon dioxide.
Yeah, so the silica from the test tube fusing with the deposited metals was sort of a problem, but it also, at first when we deposited iron, it didn't actually oxidize despite that there was oxygen in the test tube with it. And when you looked at it under the microscope, you saw that it had it was very crystallized. And so your first hypothesis was that this was because it was extremely pure iron. But then later we found out that it's probably because it's fused with the silica. So it's like a ferrosilicate, which is still cool. But it did sort of become a problem because then in order to see how pure the metals are, we needed to test to see their, how electrically conductive they were. And if everything's fusing with silica, it's going to increase its resistance by a lot. So it's going to make it harder to quantify how pure our deposits were. But you found out that just doing one pass of the laser at a time was enough, and then letting it cool, and then doing another pass. And this obviously wouldn't be a problem on the moon. It's very specific to our experimental setup. But I think it's still good to know if this was ever recreated.
Yeah, so it was actually a crystalline, it was very crystalline looking material. And it absolutely would not corrode no matter what. It would not turn into its oxide forms. We tried everything. We tried even salt water at one point. We did realize, because the electroconductivity was so poor, that, possibly we're melting the glass in with the actual iron. And we just dialed that back. We just, modified our settings so that it was a single pass and that it came in at a different area, so that the deposition area was the same, but the actual area that the laser came in with was a different area. Therefore, it didn't actually give it time to fuse. And the metal was absolutely pure. Iron showed 8 ohms at one point, and it's metallic. You can see it. So since we used a pure, iron monoxide to do this with, it's reduced iron. It's just keeping the temperatures at a place where everything plays nice is the tricky part. But we were able to actually do that. There's only so much heat that we can put into the system before even quartz or borosilicate will end up, cracking it. And trust me, we cracked many test tubes. Finding out the correct focal length, the correct steering speed, the correct pulse width is pretty much the key. But these are all definitely possible. And it's not a lot different than any type of pulse laser deposition that you would, run into in the microchip industry. It's used all the time. They'll take an oxide target and they'll hit it with a pulse laser under vacuum, and energy itself will disassociate a lot of the oxygen, which gets carried away by the process and deposits the reduced metal. It's one method. It's not the only method. We plan on trying RF reduction, pulse laser hydrogen reduction, plasma reduction. Pretty much gonna try everything that we can to see what is the best method for each oxide.
And then you mentioned a few times how iron was so easily sublimated with the laser, but that actually sort of turned out to be a bit of a problem, right? For Regolith refining with a laser in this sense, which is still a surrogate for pyrolysis, but in general, it's a good data point to know that the iron almost absorbed the infrared a bit too eagerly and sort of acted as a scepter, more or less, where it sublimated because it caused the rest of the simulant around it to sort of beat up and glassify. Whereas if you removed the iron first, like using the hydrogen method, then you would have enough range between oxides to target them individually. Do I have that right?
Yeah, what we found is that basalt and iron are kind of poisons to the process. Having beneficiated the process and removing the iron absolutely makes things a lot easier. You can do iron by itself as well and be really successful with it. But when it's mixed with the other regolith, it's a very potent, almost poison. If you think about it, it's going to absorb a lot of the energy that you're trying to put in other places. Now, you can use that to your advantage if you have something that is very white, for instance, like titanium dioxide, and you start with some iron monoxide as a nucleation seed where you create the heat in that substrate, and then the heat creates a phase change in the material around it, and that phase change creates a different, the metal to absorb light differently. That's also a possibility that you can use iron for. So it's actually beneficiation is really important. One of the methods to do all this, once after iron is done, is electrostatic beneficiation. Also after calcium reduction, you really kind of eliminated a lot of the impurities for the next process along the way. So you do have an end-to-end process that does produce everything in its usable form instead of a wasteful byproduct.
So I'm imagining that the step-by-step industrial process might be something like, first you gather regolith, and then you do hydrogen reduction, and you pull out the iron, and then with a magnet, and then you would maybe do calcium reduction, so then you're left with an alloy cake that then you could put it through the pyrolysis process, and you'd be able to sublimate those metals at much lower temperatures. And then you obviously need to return your calcium oxide. You were able to use the laser on the slag or on the alloy cake that we got whenever we did the calciothermic reduction. And you were able to return golden pure calcium for a second before it reoxidized with the oxygen in the tube. But it showed that pyrolysis should also work on this calcium oxide so we can get our closed feedback loop.
Yeah, so in the initial phase, you're going to need a lot of calcium. So you're going to start with electrolysis probably. But once you already have that calcium oxide and you have it in your process, then then you can use either pyrolysis. I would imagine in the initial sense for production, you would do some electrolysis just for calcium. You could avoid the electrolysis process and go straight to pyrolysis, but you're going to have some difficulty with the calcium efficiency-wise. You're going to have to reach some pretty high temperature.
Well, according to the -10 atmospheres, 10 to the -10, calcium oxide sublimates, thermally decomposes and it sublimates at about 1550 degrees Celsius, if I remember, which the molten oxide electrolysis is done at 1600 degrees. So it's like a 50-degree difference. What could do lower temperatures would be molten salt electrolysis, calcium chloride, and you dissolve the calcium oxide in it. And I think it's 800 to 850 degrees Celsius for that, which is half the temperature. But then you're also dealing with, molten salt and the how corrosive those are to the refractory inside the electrolysis reactors. So it's a trade-off for sure.
Yeah, I don't think that electrolysis is like my favorite solution to the problem due to its complexity and corrosiveness. If we can find a way around that, that would be the best. That's what I believe is currently looked at in bulk for that system. I really believe that there needs to be more research into pyrolysis for this. And
yeah, sorry, I wasn't trying to correct you or anything. I was just
I was just you're asking me like the order of which it should be done. So I was just thinking of the system.
I actually agree with you that electrolysis, because it has a higher TRL level, and it's a good way to kickstart this. And we know we could probably at least target calcium oxide. Like the problem with electrolysis is the overpotential problem, to get like precise elements, you sort of have to run it through several times. And it's not even clear to what extent that is actually, even doing that, how much of a system that actually is. But here we're seeing that like pyrolysis essentially worked, like with the laser,
No, we showed that it works. Just reaching those temperature, on a massive scale, it has its hurdles. And I'm not saying that it's not possible in any way. We did show that it's possible. The complexity around that might even be less than electrolysis. Who knows? The one reason we didn't explore electrolysis itself is because it's already well known here on Earth, and the main reason is because it's incredibly destructive to your equipment and very caustic.
And then I guess I was going to just mention so the audience isn't confused. We talked about iron being a poison for this laser stuff, but this laser stuff is a surrogate for pyrolysis. So it wouldn't really be a problem for pyrolysis. It's more of a problem for laser refining, just because it absorbs the infrared so easily. Where it does sort of apply is in this experimental setup as lasers as a surrogate for pyrolysis. I just wanted to clarify that this is where the laboratory is different from industrial process.
Exactly.
Yeah. And really it's like a poison for the experiment, specifically because of the lasers. Anyways, yeah, I'm kind of splitting hairs here, but you already commented on it, but after building up the settings library by testing the laser on individual oxides, the final thing was to put it all together and try to demonstrate multi-oxide single tube selective deposition. And were we successful?
Yeah, we were successful. We were able to do titanium and iron. They're pretty much two oppositely colored particles. They're going to be the darkest and lightest metals that you can probably reduce with a laser. And we were able to reduce them. Now, obviously, the one ablation rate is a lot higher than the other. So they did show electroconductivity, but higher on the iron, because the iron obviously deposited more. So inherently, there's some problems in trying to do them both at the same time.
So you don't think we could do it? You would have to beneficiate it, or do you think we could do it on bulk regolith, which is, a mix of more or less 12 oxides?
Yeah, so there needs to, I mean, that's a tough question. So technically, yes. Has it been done? No, only with the iron, titanium. And then on the bulk regolith, what I ended up with is mostly iron and magnesium. So there is some limitation on the temperatures of which these are going to volatilize at are going to dictate, which ones are deposited first. So, in theory, yes, if you did these and you had a moving substrate, let's say, yes, you could absolutely do them selectively. It just needs to be refined that way. You're not going to hit the regolith with a laser at different pulses and get, a nice stripe of oxides. They're going to kind of deposit, one after another on top of each other. So, if you can account for that, yeah, then that'll be done. But if you had figured out a way to move the substrate, which is just, something very technically easy to do, then yeah, technically you probably could reduce at least all the ones that we've reduced so far with laser.
Yeah, well, I mean, needless to say, these are great results, and I think they're quite a big contribution to this field of research. So I cannot thank you enough. I mean, but I think these are just the tip of the iceberg in many ways. And in general, this field of astrometallurgy is still incredibly underdeveloped. So my question to you is, what's next? What should we do now going forward?
Well, research and development is obviously the first, but like anything else, the more minds you have working at something, the more out-of-the-box problem solving you have available to you. But what it really does is it opens up other possibilities. One of the things that, I didn't think that would be actually very viable, which I'm going to be trying, is selective hydrogen laser reduction. I really think that actually might solve a lot of problems. Maybe we can get it all down into one actual process, but we'll never know unless we all try to find out. And so, if anybody, thinks that base research is just not something that they can do because it's too expensive or it's too hard. It's really not. You think of a process and you create solutions around it. And that's the key to, discovering new methods for being able to discover new processes.
Yeah, so, I mean, test tubes are relatively affordable, and you were able to achieve, I think it was 10 to the negative third torr. I'm not sure what that is in atmospheres, but it's quite a high vacuum. It's not ultra high, but it's high enough that it's a decent vacuum for cheap. And you're able to do these very, violent thermal reactions in them. And then galvo lasers have become a lot more affordable lately. I mean, they're still not cheap, but this is something that, an average person probably has access to.
Yeah, thinking, outside the box is what's going to really drive this industry. I mean, finding, a profitable industry for lunar material is not going to be that difficult if you already have something that can make anything you pretty much need on demand robotically.
Yeah, so hopefully this can inspire more research. I imagine obviously you would probably want to have some understanding of lasers and vacuum systems. I don't want to say don't try this at home, but I also don't want to just encourage everybody to do it. So, some personal caution and care should be advised. But, if you do try some cool experiments in your garage within this field of astrometallurgy, get in touch with me. My email is on the channel's about page, and I'd love to share it.
Yeah, safety is important because you are dealing with the laser, glass, and vacuum, and all those things combined can be a problem.
And going forward, you mentioned combining hydrogen with the laser reduction. So combining these two processes rather than hydrogen as the first step and then lasers or pyrolysis as the second step, you're now looking at combining the two. And then you also mentioned like RF, like plasma. Are those two separate? It's the same.
Yeah, they're separate. So some of the more known ways of disassociating oxygen from an oxide is using plasma. It's in the microchip industry or in some industrial processes. Plasma can reach the temperatures needed, and it can also exist in the pressures that are necessary for the environment. I'm gonna try some plasma reduction, some plasma hydrogen reduction, and try some pulse laser hydrogen reduction, some microwave reduction, and we're gonna see the differences in efficiencies and what other metals they might reduce that we might have been missing along the way. If we can, incorporate this all into a single process, then that would be the ideal process.
All right, so we're definitely going to have a follow-up, a part 2 on this when we figure those out. So, but until then, stay tuned, and thank you again for everything.
You're welcome. Thank you for having me.
Well, I think this might actually be my longest video ever, and it's sort of a part 1. We made solar cells, we plan to do plasma refining, and we plan to send samples from these experiments to fellow YouTuber and scientist extraordinaire, Neptunium, who is able to perform wet chemistry third-party analysis and let us know the exact nature of our reduced samples. But in the meantime, go check out his channel. He has lots of cool videos that definitely deserve more attention. If you made it to the end, here's the link to the Anthrofuturism Discord server, where we will have a channel in which you can access all the footage, documents, and data associated with these experiments. Normally, the Discord is reserved for those who care enough about this topic to become a channel or Patreon member, or at least visit the Patreon page to see the link, so they don't have to actually join and spend money. But the reason for this kind of barrier is so that it acts as a sort of filter for those serious enough about lunar development, so we can avoid spam and bad faith discussions and crypto scams and whatnot. But I think if you watch this entire video, then that basically acts as a filter in itself. So come join our lunar development crusade. Of course, maybe you just scrolled to the end of this video, in which case you should still join, so that we can right your ways and convert you into a righteous member of our lunar flock. I know typing a link in manually is a pain, so I put the link at the bottom of the description page, way down underneath past the credits where few humans dare to go. I know this is excessive as fuck, but I'm trying to keep something of a smaller, tighter knit, more exclusive community here, mostly just to stroke our own egos. Normally, I would ask you to like and subscribe, but apparently those aren't enough for YouTube, so now they had to introduce a hype system to make channels under, I think it's 100k subs, more competitive. So if you can hype this video, that would be awesome. The hype should be free. I think you get like 3 per month or something. I mean, don't spend any money doing it. If you're going to spend money, I'd rather you become a patron or channel member, so don't waste $1 on what is essentially a super like. But if it's free, then let's see if it might help this video go much further. Okay, I'll shut up and end the video now. As always, thanks to the Patreon and channel members who support this, and thanks a million to Robert from 2RK Innovations for lending his expertise, time, and equipment to progressing this field of research. More experiments are ongoing, so we will have 1 or 2 more follow-up videos. Until then, stay toned, and thanks for watching.